Hi everybody! Once again, we are going to be talking about the atom. The atom is the smallest building block of matter. Let's talk about the history behind the atom. So there's this guy named John Dalton. He created a theory about the atom, and we call it Dalton's atomic theory. First, all elements are composed of atoms. We know that already from the previous unit. Second, all atoms of an element are identical. Now I'm going to circle number 2 because, as we'll see later in this video, this point is technically wrong since atoms of an element can have slightly different nuclei, and we call these variants of an atom of the same element isotopes. Third, atoms of an element are different from atoms of other elements. So this goes back to the discussion of how the element describes the type of atom we have, so therefore different elements have different types of atoms. So now let's get on to number 4. In a chemical reaction, atoms are rearranged. So let's take a look at this example. In this example, one molecule of CH4 or methane and 2 molecules of O2 or oxygen gas combine and rearrange to form one molecule of carbon dioxide and 2 molecules of water or H2O. So let's also remember the concept of the conservation of mass. On both sides we have one carbon, as shown here and here. We have 4 hydrogens, so let me just undo that. We have 4 hydrogens here and 4 hydrogens here. So 4 hydrogens and 1 carbon. And we also have 4 oxygens on both sides. So overall, mass is conserved. And how does it relate to number 4? Well, when atoms are rearranged, they are neither created nor destroyed, just like the law of conservation of mass says. So for example, this carbon right here does not become created nor destroyed. It simply moves into here and pairs up with oxygen atoms instead of the hydrogen atoms that it was attached to before. So that is the literal definition of a chemical reaction. I also wanted to talk about the numbers that are involved over here. So the subscripts, meaning the numbers that come after the elements, indicate how many atoms there are inside the molecule. So for example, this 4 tells us that there are 4 hydrogen atoms inside the molecule CH4. And on the other hand, the number in front, aka the coefficient, tells us how many molecules there are in the reaction. So in a reaction, it looks like there are 2 molecules of water being produced. So we'll get more into the coefficients and the subscripts later on in future videos, but this is just an introduction. Now, last but not least, a compound is formed when 2 or more elements are combined. Well, isn't that the literal definition of a compound, which was defined in Unit 1? Well, yes, it is. And as a result, Dalton's atomic theory, for the most part, is valid. And yeah, let's move on to the next topic. We have to talk about what makes up an atom. This right here is an atom. Or, I mean, a model of an atom. So I already told you that a nucleus and electrons make up the atom. But what exactly makes up this quote-unquote nucleus? Well, there are 2 things actually. The nucleus is made up of positively charged protons, as well as electrically neutral neutrons. So the proton, neutron, and electron are subatomic particles because they are smaller than the atom, which is why they're called subatomic, because, they're under the size of an atom. So we write protons as P plus, we write neutrons as N with a 0 as a superscript since it's electrically neutral and doesn't have either a positive or negative charge. Last but not least, the electron can be written as E minus because it is negatively charged. And to be more specific, a proton has a +1 charge, a neutron has a 0 charge, and an electron has a -1 charge. Now, let's talk about the size of these subatomic particles. A proton and neutron are nearly identical in mass, which is why I wrote the equal sign, but an electron is actually equal to 1/1863 of the mass of a proton, which means it is super small in terms of mass. So let me ask you something. Why does the atom stay together and not fall apart? To answer this question, I have to erase everything that's surrounding this atom because it's kind of getting messy. So let's look at this. Why does the atom stay together? Well, all in all, it's because opposite charges attract. The protons, which are positively charged, and the electrons, which are negatively charged, are attracted to each other because they have opposite charges. So that's why the electron doesn't just, run away, and instead it likes to stay with the nucleus because there are positively charged protons that it is attracted to. Now, another question might be, why do protons and neutrons stay together? Well, that's completely unrelated to charges. Instead, it is related to something called the strong nuclear force, which is a super duper strong force that keeps protons and neutrons together. And I won't talk about that because it's not really related to what we're talking about right now, and I wouldn't want to waste your time. So let's move on to some history lessons. So electrons were discovered by J.J. Thomson, and he did this when he shot this negatively charged ray, which is indicated by purple, through a tube, and he saw it bend right there. And why did it bend? Well, this plate right here was negatively charged, and since this ray was negatively charged as well, the ray actually wanted to move away from the plate, so that's why it kind of went in a downward direction. And why did it do that? Well, remember, opposite charges attract, while same charges repel. So I basically taught you the basics of electricity. Now let's look at the second experiment. Millikan determined the charge of an electron by doing this oil drop experiment, which we won't get into, but basically he discovered the charge on the electron. Now protons were discovered by Rutherford when he shot positively charged alpha particles and saw that they were deflected by the gold foil. So in other words, he knew that the gold was composed of gold atoms, and by shooting this positively charged ray and seeing it being deflected, he obviously concluded that there must have been a positively charged particle in the atom, which we know now as the proton. So, when he shot it there, it got deflected because this was positively charged and the protons are positively charged. So in this image, it got deflected as shown right there. And now let's look at our last guy. James Chadwick discovered the neutron. Now, I won't get into how he did that, but just know that he discovered the neutron. Now, you might be wondering, how large is the atom? Well, the radius of the atom is between 30 and 30 picometers. This is 10 to the negative 12 meters. So obviously, the atom is super, super, super duper small. And we can also write the radius of an atom in terms of angstroms. 100 picometers is equal to 1 angstrom. So that's just something fun to know, and maybe it'll pop up in the future. Let's now talk about the structure of an atom. Scientists have developed models to show what an atom looks like, since we can't really see it very clearly, even with advanced technology. In 1803, John Dalton, which is the same guy who developed the atomic theory that we talked about, thought that the atom was just a sphere, hence the sphere model. And then we get into 1904, where J.J. Thomson, the guy who discovered the electron, developed the plum pudding model, which is basically a positively charged sphere, but with electrons scattered throughout the sphere, as shown here. Now we get into 1911, where Rutherford, the guy who discovered the proton, thought that the atom was basically just empty space, but with one super dense and super small positively charged nucleus in the middle. And the rest of the empty space just had electrons kind of floating around, as shown here. So this model is called the nuclear model. Now we get into 1913, where Niels Bohr created the planetary model. It was basically Rutherford's model, but the electrons don't just move randomly. They actually move in orbits, such as the circle right here, with certain amounts of energy. Now, our last model, which we commonly use today, is made by Schrödinger and is called the electron cloud model. This model is basically Bohr's model, but the electrons are actually impossible to locate. So scientists determined that there were actually these clouds or spaces that were most likely to hold these electrons. So an electron may be more likely closer to the nucleus than it would be maybe out here. So the electron cloud model is based on probability, and it doesn't exactly tell you where the electron is. It only gives you the cloud or space where you are most likely to find an electron. In this case, the most likely space to find the electrons are in this blue sphere right here. And remember, these electron clouds are three-dimensional, unlike Bohr's model, which was kind of two-dimensional because orbits are two-dimensional, right? And you know, in 1932, the quantum model was updated, and the quantum model is just another way of saying the electron cloud model. So this model was updated to include neutrons, which was discovered far later in history. Now let's talk about atomic mass units. It's a unit we measure in place of grams because grams is honestly too large of a measurement to measure something as small as an atom. So instead we use an atomic mass unit, which is very, very, very small compared to a gram. Now let's talk about what exactly an atomic mass unit is. Well, one atomic mass unit is exactly equal to 1/12 of a carbon-12 atom, which can be also written like this, and I'll show you how to write it like this very soon. And something else you should know is that one atomic mass unit is approximately the mass of a proton, which is approximately equal to the mass of a neutron. So keep that in mind. And let's look at how this nuclear symbol works. So we call this format of writing elements a nuclear symbol. So what does this 6 represent? Well, this 6 represents how many protons there are. So in this drawing, we see 6 plus spheres. So it has 6 protons. And that's what the 6 means in the nuclear symbol. Now, what does the 12 mean? Well, the 12 just tells us how many neutrons and protons are in the nucleus. So in the image, we can see 6 gray spheres, which represent neutrons, and 6 plus 6 is 12 neutrons and protons in total. So that's why the 12 is there. So these have proper names. The number of protons is also called the atomic number, denoted by the letter Z. And you write it to the left of the element, and it's a subscript. Now, on the other hand, our mass number is the number of protons and neutrons, and it is denoted by the letter A, and it is written as a superscript, which means it's like above. Also, I wanted to add that an atom is electrically neutral, which means that our number of protons and our number of electrons, which I will write in yellow instead, are equal, because if you have 6 minus 1 charges and 6 plus 6 charges, then they add up to 0, which means they are neutral. So how about this? Let's just count how many electrons there are. There are 1, 2, 3, 4, 5, 6. And that proves my point that the number of electrons and the number of protons are equal in a neutral atom, such as carbon 12. So in an atom, the number of protons is equal to the number of electrons. That'll be very important in the future. Now, let's talk about what exactly defines an element. In previous videos, I told you that an element describes the type of atom we have, but what is that thing that we look for that differentiates between the different atoms? Well, the truth is that an element is dependent on how many protons you have. So, in other words, the atomic number, or the number of protons, determines what type of element you are. So, for example, if you have 6 protons, you will always be called carbon. And another example is that if you have 1 proton in an atom, you will always be called a hydrogen atom. And here's where the tricky part comes in. For an element, the number of protons stays the same, since the atomic number determines what element you are, but the number of neutrons can change. So for example, in carbon 12, we know we have 6 protons, but we have 6 neutrons, and this 6 neutrons can vary. So what if I wanted a carbon atom with 8 neutrons? So if we had 8 neutrons instead of 6 neutrons, what would this number be? What would our mass number be? Well, if we have 8 neutrons and 6 protons, 6 plus 8 is 14. So this would be carbon 14, while this would be carbon 12, which is written right here. And to write the nuclear symbol in letters, you simply write the element and you put a dash, and then you put the number of protons and neutrons combined, aka our mass number. So the 12 is that, and carbon is just the element C. So here's one important terminology. Carbon 14 and carbon 12 are called isotopes. So I'll write isotope down here. Isotopes are just variations of the element, and they vary by the number of neutrons. So for example, carbon 14 had 8 neutrons, while carbon 12 had 6 neutrons. So notice how they vary by the number of neutrons, and that's what an isotope is. So this goes back to the point of the very beginning where I said that number 2 was wrong, which said that all atoms of an element are identical. And the reason why all atoms of an element are not identical is because of this fact that elements can have varying number of neutrons, and that makes them have different kinds of isotopes. So the fact that all atoms of an element are identical is actually false. So you can go back to the beginning of the video to see that, but now we are going to move on. So this diagram right here is called the belt of stability. So let me spell that out. So the belt of stability tells us the isotopes that are stable, meaning the ones that don't radioactively decompose or change over time. Because if you have too many neutrons, you might decompose because you won't be stable. So this belt right here tells us the places where an atom will be stable. So for example, if you have 60 protons, denoted by the letter Z, which is our atomic number, if you have 60 protons, you are most stable when you have about, I'd say, 85 neutrons. So this belt of stability tells us if you have a number of protons, it'll tell you how many neutrons you need to generally be stable. So here I created a rule, or a general, I guess, trend that occurs that tells us if an atom is stable or not based on the number of neutrons and protons. So we will be looking at a neutron to proton ratio. So if you have a 1-to-1 ratio, the number of neutrons and number of protons will be the same. But if you have a 2-to-1 ratio, for example, then you'll have twice as many neutrons than protons. So now that we've got that out of the way, let's try to figure out what this diagram is saying. So for elements that have an atomic number of between 0 and 20, a 1-to-1 neutron to proton ratio will be stable. So for example, carbon 12 will be stable because it has 6 protons and 6 neutrons, and that's a 1-to-1 ratio. Meanwhile, something like carbon 14 has 8 neutrons and 6 protons, and this is not a 1-to-1 ratio. This is an 8-to-6 ratio, or when simplified, a 4-to-3 ratio, or when even further simplified, a 1.33 to 1 ratio. So in order to simplify ratios, you basically just divide both numbers by, for this one, I divide by 2 on both sides, and in order to simplify further, I divide it by 3, and I divide it by 3. So that's how you simplify ratios, and as you can see, 1.33 to 1 ratio is not equal to a 1-to-1 ratio. So that's why carbon 14 is unstable. So let me draw a red circle around it to show that it's unstable. So these ratios will tell you how many neutrons and protons you need in order to be stable. So let's look at the next ratio. So if you have between 20 and 40 protons, then generally a 1.25 to 1 neutron to proton ratio will be stable. If you have between 40 and 50 protons, then a 1.4 to 1 ratio for the neutron to proton ratio will be stable. And last but not least, if you have between 50 and 80 protons, then a neutron to proton ratio of 1.5 to 1 will be stable. And notice how we don't look at anything past 80, because once you're past 94, as we'll talk about later, you are generally going to be radioactive and unstable. So we don't need to use the trend anymore, because there are technically no more, I guess, isotopes that are truly stable. And I mean, you could look at this, but the truth is that anything beyond 94 will generally not be as stable as the atomic numbers before that. So let's move on to our next topic. Let's do one practice problem with nuclear symbols. What if I wrote uranium-238? How would you write its nuclear symbol? Well, if you check out the periodic table, you will see that uranium has 92 protons. And remember what I said about the number of protons and electrons, that they are equal, even though it's covered up, but it's still there. So if it has 92 protons, then it has 92 electrons. Now, how can we figure out how many neutrons it has? Well, we can first write out the nuclear symbol, the element name, with 92 protons as its atomic number, and its mass number is that, and it's 238. So how can we figure out how many neutrons there are? Well, we know that the number of protons and the number of neutrons is equal to the mass number, which is 238. And we know that the number of protons is 92. So we could do some algebra, minus 92, and we get that the number of neutrons is equal to about 146. So the number of neutrons in uranium-238 is exactly 146 neutrons. So now that we covered that, let's move on to our next topic. So we have talked a lot about elements. You have seen elements like carbon, oxygen, iron, and even hydrogen. And all those elements come from this periodic table. Now, this periodic table has 118 elements, and the number will only grow in the future as technology advances. So, our rows, so we are going to have rows. So, a row is called a period. So, I'm going to write period. And a column, such as this column, is called a group or family. The whole number, as shown maybe right here, is the atomic number or the number of protons you have. So in this case, gold has an atomic number of 79. We won't worry about this other number. We will talk about that number in the future. So let me erase everything and clear all the ink. So let's talk about the classification of these elements. We usually classify elements into groups or columns. So the main group elements are groups 1, 2, 13, 14, 15, 16, 17, and 18. If you ignore the ones from 13 to 18, you basically get 3 to 8. So if you think about it, the main group elements are from 1 to 8. So the elements that are stuck in the middle, aka families or groups 3 through 12, are called transition metals. So here I labeled them for you as shown right here and right there. So now let's get into the specific groups. So let me clear the page. So I'm going to clear the ink and I am going to start labeling the different groups. So group 1 are the alkali metals as shown down here. And one exception is hydrogen. Hydrogen is not an alkali metal. Now, our second group, group 2, are called the alkaline earth metals as underlined down there. Now, next we have the post-transition metals, which are generally located in groups 12 through 16. And since this color is gray, it just includes all of these elements. So now let's actually separate these groups into different names. So we are going to ignore group 12 for now. Let's focus on group 13. Group 13 is called the boron family because the first element in that group is boron. Now group 14 is the carbon family. Group 15 is the nitrogen family. Group 16 is the oxygen family. And group 17 is not called the fluorine family. It's actually called the halogen family. And don't ask me why. I'm not sure myself why it's called that. And last but not least, group 18 is called the noble gas family. Noble gas family. And these are noble gases because they tend to not react, and as a result, they're called noble because they are noble to their own element and they don't like to mix with other elements. So now let's look at a different group. Let me clear the ink once again, and let me draw a staircase. So let me draw this very nice staircase, and this staircase will tell you where the metalloids are. Now, metalloids are also called semimetals, and they are called that because they have properties that are similar to metals. At the same time, they have properties that are similar to the nonmetals, which we will be talking about later. So our metalloids are boron, silicon, arsenic, germanium, antimony, tellurium, and polonium. I don't know why this chart says that polonium is a post-transition metal, but polonium is a metalloid. So acetine is non-metalloid. Acetine is actually a halogen, so ignore the coloring there. Sorry for that. So everything to the left of the metalloids are called metals, and everything to the right of these semimetals or metalloids are called nonmetals. And that's just one word, but I just kind of separated it into two lines. And hydrogen is a nonmetal, which is why it is not an alkali metal, as all these other guys are. Now we have two special periods. The first period consists of our lanthanides because the first element in the period is lanthanum, and the second period shown here are called the actinides because the first element in the period is actinium. So let's talk about why some elements have weird symbols. For example, gold on the periodic table is defined by the symbol Au. Now, gold doesn't have anything to do with the word Au. So why is it called Au? Well, Au comes from the Latin name aurum, which stands for gold in Latin. So Au from here goes here, and now it's obvious. Meanwhile, other elements like oxygen have intuitive chemical symbols. So oxygen is O because oxygen starts with the letter O. So most of these chemical symbols are intuitive, except for a few. So now let's move on to some important facts. Oxygen, aluminum, and silicon are the most common elements in the Earth. So I'm going to write Earth here. Now, in our atmosphere, oops, I didn't finish writing the word Earth. In the atmosphere, nitrogen, oxygen, argon, and carbon dioxide are the most common compounds in the air. So nitrogen makes up 78%, oxygen 21% about, argon about 1%, and next is carbon dioxide with a measly score of 0.038%, and everything else is just, very, very small. So now let's talk about synthetic elements as shown here. Synthetic elements are elements that cannot be found in nature. They are elements that are found when you make them in the laboratory artificially, hence the word synthetic, which means man-made. So any element past atomic number 94, which is plutonium, will be a synthetic element. Now, let's go on to the next topic. You might be wondering, why do I call oxygen O2 instead of just O? Well, some elements like O always exist in nature as a pair because they are more stable that way. So O2 is more stable, as a pair of two oxygen atoms than alone. And we have a total of 7 elements that always pair up. So these elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So we have 7 elements that pair up. Now, all these are gases except for 2 of them. Bromine, Br2, is a liquid, And iodine, I2, is a solid. The last thing I want to talk about are allotropes. So let me write the word allotrope. Now, allotropes are just elements in nature that exist in different forms. For example, sulfur exists naturally as S8, but it exists in different forms, even though it has the same chemical formula, having, 8 sulfurs. They are shaped differently, which is why they're different. So S8 exists in 2 forms, in a rhombic form, which, is kind of bent, and in a monoclinic form, which is basically just a flat octagon. Another element with famous allotropes is carbon. So carbon is C, as shown here. So carbon can exist as diamond, which is shown here, graphite, which is shown here, buckyball, which is shown here as a ball-looking structure, and as nanotubes. And they're called nanotubes because they look like tubes. So allotropes are just variations of an element that vary because of the different structures they create. So in sulfur, the allotropes for sulfur are shaped differently, while in carbon, the atoms are also shaped differently, which is why you have these allotropes labeled A through H, but we only talk about 4 of them because they are the most famous ones. Alright, thanks for watching and have a nice day.